All right, so I'm going to go ahead and get started with the webinar today. Thank you everyone for attending. You are attending the Powering Geospatial Intelligence with Synthetic Data webinar hosted by Rendered.ai. And I'm really excited to get the chance to not only give you a bit of an update on what we've been doing at Rendered.ai, but also to have my colleague Dylan present to you some of the extra stuff that we're doing to help customers get efficient fast with synthetic data. So today on the webinar, it will be yours truly. I'm Chris Andrews, the COO and head of product for Rendered AI. I've got more experience than I'd like to admit in geospatial, 3D, AEC, and a variety of other domains. And of course, you can always ping me at chris@rendered.ai. And then I'm really pleased to have Dylan Harkness with me on the webinar today. Dylan is one of our customer success software engineers, and he's fantastically customer oriented. He typically is using Python coding and 3D modeling to help implement the simulations that actually drive synthetic data for our customers' specific needs. And if you want to follow up with Dylan after the webinar, his email is just dylan@rendered.ai. There are a lot of experts on the call today, and I do not need to go into the nitty-gritty depths of computer vision applications in geospatial AI. But sometimes it's nice to just give a high-level overview and kind of level set what we're talking about. So typically, when we talk about using AI in geospatial intelligence workflows, what we are talking about are some kind of classic things like identifying what an image is or what's in it, identifying objects and tracking them, identifying unusual scenarios or circumstances or objects, and then doing things like classifying areas and instances in imagery. We focus typically on computer vision imagery. That's the domain our customers are in, our users are in, and we've actually amusingly heard people say things in the last few months like AI is solved in geospatial, which is obviously not the case. In fact, what we hear over and over is that there are challenges or circumstances that constantly drive our customers to be looking at different data sets, alternatives to existing data sets, new ways of using data sets. And these range everywhere from the fact that maybe a customer is looking for really rare objects or scenarios to it's just really hard to get data of the things that they won't need to get enough data of to train algorithms. They may even be looking at things like, it's a really common object, but it's not often captured from a particular pose or orientation. And of course, labeling and annotation of imagery can be labor intensive. It is always labor intensive. And in some cases, such as for some of the newer or more novel sensor types that we're seeing, like SAR and hyperspectral imaging, those are also expertise intensive in terms of interpreting and labeling them. All of these challenges really point to the fact that AI in general, as everybody knows, has a big limitation, which is data is an essential component for training and validating and deploying AI. We typically see two different sides of the AI data limitation problem. One is that not having enough data or not being able to access data can actually limit innovation and impact cost and time to market. Many of our customers are actually using us to try to get to market faster or to try to do something to train algorithms before they even can touch real sensor data. And the other side is we often see customers trying to overcome specific issues like bias in data sets, where, for example, a customer may not be able to get enough images of a particular type of object that they're looking for or tracking. Or in some cases, customers are looking for more variety in the objects that they're looking at so that they can tune accuracy in algorithms. And so on this side, we typically see those customers looking at performance of algorithms. Rendered AI provides a platform as a service with compute and content that is kind of bucketed in two different categories. Our fundamental PaaS is a classic platform that wraps complicated, repetitive cloud capability into nice experiences, both through APIs and then through a web interface, so that customers can really focus on the task at hand, which is configuring and generating synthetic data to generate computer vision output, and not have to worry about cloud infrastructure setup and management. On top of the platform, we also provide some pre-configured and customized channels, that we call them, which are basically synthetic data applications that are intended to generate large amounts of data through the PaaS for specific computer vision applications. And you see a few of those here, and you'll see a few more later in the talk. And one thing I will point out is that I believe in this deck, all of the imagery that we show is imagery that's been spit out from Rendered, that's been generated with Rendered. In some cases, we will use a combination of real 2D imaging, such as in satellite imagery backgrounds, with 3D models, but everything that you see will have been processed through Rendered.ai with the intent of satisfying a customer's computer vision application. What we've seen is we've actually had many happy customers since I joined Rendered 3 years ago, and we released our platform about 2.5 years ago. We've seen customers come back to us and report that they can generate physically accurate synthetic data at about 25% the cost of trying to acquire real data. And some of those same customers have not only said that they were able to generate data more cheaply than acquiring a real data set, but they then were able to go on and use our platform to create more data with more diversity and variety, and experimental variety in some cases, than they could have ever gotten out of acquiring real data sets. Our platform provides a configurable interface for easily reconfiguring channels, so that you can experiment with the diversity in the data that you're generating. Our platform is collaborative. It's got a multi-user experience, so that you can have more than one data scientist, computer vision engineer in the platform at once, working on your synthetic data application. We provide a variety of other tools out of the box for things like dataset comparison. But one of the most important things about providing a platform as a service is that we are not attempting to do it all. We rely on partners, as you see on the right here, who in some cases provide best-in-breed simulation and rendering capability, so that we can actually maximize customers' ability to get to the imagery they need using an appropriate simulator and content that fits their specific problem set. One of the exciting things that we're super happy to talk about, that it's a great example of this, is that ANSYS has decided to allow us to explore using PerceiveEM, which is one of their simulation toolkits for things like looking at placement of radio towers in large cities. They've decided to allow us to use this and package it for availability for customers in Rendered.ai for doing things like actually generating really large scenes of synthetic aperture radar. SAR, as some of you probably know, is a rapidly emerging, becoming pretty popular data set type. SAR is interesting because SAR satellite sensor can actually see through clouds, and SAR works at night, so you don't have some of the limitations you have with RGB type satellite imagery. We are actually able to now generate very large SAR scenes with the help of the PerceiveEM simulator and the help of the ANSYS team. We've got some scenes that have gone up to about 5 kilometers by 5 kilometers, and we believe we can get even larger. A really cool workflow that you can see in the image here is what you see is an actual reality capture image of a defunct Air Force base, and that has been combined with some 3D models of tanks in this case. that are, you can see kind of in the upper center of the image. And those have been processed together through PerceiveEM, and you actually get a very interesting, compelling SAR image output. If you were trying to train for, say, detecting movement in vehicles in SAR imagery, this really opens up the possibility of allowing you to access a huge diversity of SAR imagery that you're unlikely to ever be able to get from physical capture. We have an upcoming webinar on this on August 22nd at 10 a.m. And if you're interested, you can follow up with me, or there will be other information at the end for following up. Fundamentally, what we're trying to enable with Rendered is essentially an iterative loop workflow for multiple users to work together to create data that actually helps improve their algorithm training and validation. So we provide a user-friendly experience for a data scientist to actually configure synthetic data channels and generate data, but that's predicated by cloud compute capability underneath, and also an SDK and framework for simulation engineers, synthetic data engineers to actually package simulators, scenario and scene configuration, and 3D and 2D assets so that our customers can actually build the appropriate simulation that fits their use case, deploy it to the cloud to be able to be run many, many, many times, and to do so in an environment that offers configurability with drag and drop tools that make it an immediately easy tool for a data scientist to use to do something novel for them, which is to actually generate data. As you can see, we have worked with a variety of different customer types over the years to generate a huge variety of imagery that is used in a wide variety of real world intelligence as well as geospatial intelligence workflows. The imagery that comes out of Rendered.ai is typically produced with annotation and masks. In some cases, masks are not as easy to generate for some things like synthetic SAR information. We have access to an X-ray simulator for security type X-rays. You can see that we've been able to do a wide variety of urban and natural environments, and we can create those with a huge amount of variability and also knowability about exactly what is at what pixel in each image. We've got some efforts to move more into interior spaces. That's been driven by some customers who've been looking at placement of objects in interior scenes. And then we've also generated some tech for doing things like reconfiguring large sets of assets in large landscapes. And what you can also see is that these assets can then be used with physically accurate simulators to generate a wide variety of imagery for the same kinds of scenes and assets. Okay. I'm going to quickly talk about a couple of customer stories, and for me, the real meat of this talk is to get to Dylan and have him show his workflow. So you'll forgive me if I go through a little bit quickly. We've been working with Orbital Insight, now a wholly owned subsidiary of Privateer, for about 4 years. With Orbital Insight, with our help, won an SBIR a few years ago to start to look at if you could use synthetic data to train algorithms to look for things that humans typically find very difficult to look for. The project started out looking at construction cranes and construction trucks that can be in a couple different configurations that have kind of vertical diversity that can be difficult for a human to recognize. And what we were able to show in the very earliest project was a pretty significant improvement in algorithm performance for detecting these types of vehicles in a very popular data set called xView. That initial success has led us into subsequent follow-on SIBR projects on the same SIBR, And we're super excited to be continuing to work with Orbital Insight Privateer as we move forward. We've been working with BlackSky for a couple of years. We're proud to say that they're another one of our repeat customers. For BlackSky, they run into classic challenges of sourcing adequate quantities of imagery for rare object detection. They are trying to apply algorithms and train algorithms for different sources of imagery from a wide diversity of sensors, and sometimes even diversity of sensors for the same type of sensor modalities. And they would really like to use existing data to serve as synthetic imagery backgrounds. In some cases, we found that that is one of the most effective ways to quickly get to synthetic data that actually performs very well with real data. In fact, using Rendered.ai, BlackSky has been able to detect a larger number of diverse objects and use those as training data for the BlackSky platform. So we're really happy to be working with them. The workflow that Dylan is going to talk about today was also developed for BlackSky so that their analysts could themselves prep imagery for use in the Rendered.ai platform. And Dylan's going to talk about that. He's going to use a different data set than one that BlackSky would use, but we're pretty excited to be able to talk about that a bit. We also worked with faculty, an AI analytics expert company over in the UK who had engaged in an innovation project for DSTL and through a company called Kanos. DSTL is kind of like the DARPA of the UK. They were having some challenges. Basically, their project was about trying to demonstrate that they could train algorithms for a future type of imagery collection that was going to be done by a UK MOD customer. The punchline is that they were able to train algorithms to detect what they needed to detect. They also, at one point, were asked by the customer if they could prove that they could create a failure case, a predictable failure case with synthetic data. And they actually used our tools to modify the look and feel of vehicles in scenes in a way that was kind of absurd and should have failed. And in fact, they were able to demonstrate that that did fail the trained algorithm detection. So they were super happy with us. They actually also came back and gave us some great stats on how much more inexpensive it was to use Rendered to generate and acquire data than it would have been to go out and acquire real data. We also were super happy to work with Planet. Planet, as everybody knows, is in the process of putting up the Tanager satellite flock, and that satellite flock is all about collecting hyperspectral imagery for doing things such as methane plume detection. That's a super expensive process, and they wanted to be sure that they weren't that they were making promises that they could provide some proof around. And so Planet actually worked with us not only to develop physically accurate imagery that emulated future real collected imagery with methane plumes, but also they were able to use imagery and an integration with the Rendered.ai platform to have one of their systems drive imagery generation so that they could then ingest that imagery into an AI pipeline and move it all the way through to simulated packaging for a customer. So that was a really exciting case for us. It validated many of the aspects of why we built our platform. Incidentally, the Planet project is also what drove our now multi-year partnership with RIT, and that's been a fantastic outgrowth of this project with Planet. All right, so I'm going to go ahead and turn it over to Dylan. Dylan is going to walk you through how our front-end UI of our platform works a little bit, but the real meat of what he's going to talk about is a novel set of scripts that he's built to help customers clean real imagery so that that imagery can be used for synthetic imagery backgrounds. Go ahead, Dylan.
Right. Thanks, Chris. Hi, I'm Dylan. So I'll be showing the workflow that we've sort of developed, and let me share my screen here. All right. So I'm here on the platform. First, I'm going to go and give an overview of the platform itself, just to give sort of a framework on how this new workflow we've developed has helped the process and way we develop synthetic data. So here on the platform, got a couple of workspaces here. I'll be going into this one in a moment here, but first I'd like to highlight the sample gallery. And this is a good place to start when you get onto our platform. It has a number of different applications we've developed, which we call channels. And each of these channels or applications have been developed for different sorts of domains. And each of these entries here represents a predefined workspace, which has a number of graphs and different things for users to experiment with, such as the Venus satellite sensor workspace here will use the deer stick sensor and be able to generate different sorts of images than, say, this toys and boxes one. So new users can just use this create workspace button to get access to this and start experimenting. So I'll show you a workspace I've already created here. This is for our satellite RGB application, and I'll take a look in here. This one's going to be added to that sample workspace, sample gallery pretty soon here. So take a look on our blog for any notes on that coming up. And so here in this workspace, we have a number of graphs. These come preloaded with the workspace when you create it with the sample gallery. And you can see we have things like land vehicles, aircraft, watercraft, construction, things like that. And each of these graphs has a number of nodes in them. We have our graph editor here. You can see we have a node tree, and this node tree has a couple of different types of nodes in it. We have our object node here, which is an Airbus plane. We have another red node here, which is a background. This one is for different sorts of air bases that we've pre-prepared. And these backgrounds are important to the process we'll be talking about. They're 2D planes that have been created through ingesting satellite imagery. So we've got these two sorts of objects and backgrounds. We can also do things like modify them, like applying dents to this plane here. And so 50% of this plane will be dented when we've applied this modifier here. And then we've got some other nodes here, like our line node here, which will place these planes along runways. And so it'll have a couple parameters here, such as the max count, which will determine how many are placed, and things like that. So we've also got a satellite sensor here, and this will allow users to change the parameters of the sensor, such as what the output image will be like, the sort of the resolution and things like that. And so with this graph editor, you can definitely get a lot of variation pretty quickly and do a lot of sorts of experiments with a nice visual interface. You can see we have a lot of different nodes available for users to experiment with. And so with each of these applications, they come preloaded with lots of things to play around with. And so that's one of our graphs. And once you've got a graph that you like, you can stage it, and then you can run a job of it. And so we can do, say, a number of runs of one of these jobs that I've staged, and each run will produce an annotated image with associated metadata. And you can see I have a number of jobs that I've run over here on the right, and we can take a look at some of these. We have some stats on the job, which is pretty helpful for users to know, like when they started it, who started it. As Chris mentioned, this tool is collaborative, so multiple different users who are in the same organization can see what the other ones are doing and kind of compare what things they found work and kind of review what they've created. And so here is the jobs page. And so let's go to the libraries page up here. And this is the kind of the main sort of page. This is where the output data is going to be. And in here we have the results of the jobs that have run in this workspace before. We've got things like our aircraft job over here, and you can see we have our data here. We have the images of the output. We have our synthetic 3D object, our plane, that's been put onto this satellite image background. And the output you can see we have several images here, and all of these were generated with the same graph. And so you can see that the background is different, the placement of the object is different, all sorts of different things like that. And so this is a very simple graph producing quite a bit of variation already. And so that just kind of shows how easy it is to produce lots of varied data with the platform. In addition to this visual information, we can also visualize the annotation. So we have a 2D bounding box here. We can change some of the display characteristics for these. We have the 3D bounding box. Since this was simulated in a 3D scene, it has the different corners of the 3D bounding box of the object, which can be useful, especially if you're coming at different look angles than just on nadir. We also have the instance segmentation. The pixel mask output is very useful for different sorts of applications. And so all sorts of different uh, useful bits of information about these just are ready at the as soon as you've finished running one of your graphs. So in addition to this visual output and the annotations, we also have a couple of other tools in here. We have things like analytics. You can perform different sorts of analyses on different aspects of the data, such as the mean brightness. This will look at the mean brightness across the different images, which can be useful to know. We've also got different annotation formats that can be converted, such as Cocoa or YOLO, which can be pretty useful. We also have the ability to do various sorts of domain adaptation, such as applying GAN models. Here I've used a GAN model on the aircraft images here, and this one was trained on the xView dataset, which will be kind of central to most of the data we're working with today. And you can see that we have these regular images here. They look like this, but applying a GAN can kind of close the gap and change the nature of the model. This one is making it a bit more like red earth, which is present in the xView data. And in addition to that, we also have some edge effects being applied. And this can just kind of close the gap between the real and the synthetic. And so it's just another tool in the belt for just processing your data to make sure it fits your needs. So that's most of the platform. It's pretty straightforward, and it just consists of workspaces with applications, graphs within those workspaces, and then running those jobs to create the data that you need. And so with that, I'd like to start talking about how we've used AI tools to improve this process of generating synthetic data. And so I've been talking a lot about backgrounds, and a background is a 2D satellite image usually. And so this could be a background. This is an image from the xView dataset. And you can see in here, it's sort of an urban area. And immediately you'll notice that there might be a little bit of an issue. We have a whole bunch of cars and little objects of interest in here that if we put this into the platform as is, none of these objects will have annotations because they're just part of the image. And so that could cause some issues if we use this one straight away. And so this has been an issue for folks who've been wanting to add data to our platform. And in the past, we've gone through and removed each of these objects by hand using just things like image manipulation tools. And you can imagine that with how many objects are in here, that would take quite a while. Some of our times tried to remove these have been like an hour or two just to get rid of all the objects. And so the AI tool that we've used is an in-painting tool, and I'll show you the results of that. Look at that. So all those objects have been removed. And this was done through a single script that just removes objects based on a mask. And it will use AI tools to do in-painting. And so we go from this to this. And the way that that's accomplished is through a mask that looks like this. Each of these squares is a ground truth label that was part of the xView data. And so we use that in conjunction with the image using an AI in-painting tool, which in this case is IO Paint. And then that turns into this. So all those objects have been removed, and this background is ready to be used in our platform as a background for putting objects into it. And so doing this is very straightforward. Is all you need are images, satellite images, and then some sort of ground truth data, which here I have in some GeoJSON files. And then we run a script we've developed, which is just a simple Python command. And then it will use the IO Paint tool to clean out the backgrounds themselves of all those objects. And you can see I ran it on these three images here, and it only took 5 minutes to clean out all of those objects. And so that's pretty darn quick, a lot better than the hour or two that doing it by hand would be. And really, that was a large issue. Is users would definitely want to ingest lots of images, and spending so much time on processing them just really wasn't feasible. So this script has been really helpful for both us and for our customers. Like as Chris mentioned, Black Sky is they're getting ready to process hundreds of images and integrate them into the platform. So yeah, so very straightforward to run the script. And after you've done that, you'll end up with a Blender file. And I've got one here. This is the output of that script. And if I press A and select everything here, we can see all those ground truth labels have been turned into geometry. These are what we call placement areas, and these are like locations in the background where objects can be placed. And so this area used to be a car, but now it's a placement area. And if we put this into the system, an object could be placed here. So in addition to cleaning out unwanted images, we're also taking the information about where they were and things like that, and using that to inform logical placement into the scene. Now with this one, you'll notice that there are a bunch of rectangles. This is due to xView not having oriented bounding boxes. When you use data sets that have oriented bounding boxes, like the orientation of the object will be maintained, and that's really useful. That makes it so you can have basically a one-to-one replacement of, say, a car on the street. It'll be facing the correct direction once it's been put into the platform. And so this script is really, really helpful for what we're going for with this application. And so I'll show you how you can, after generating these backgrounds, you can just put them into the platform really easily. So let's go back to the platform, and I'll show real quick how you can implement these things. Is to first begin, we need to have a volume, and volumes are just repositories of files that are available on the platform. Here with this workspace here, we have a number here. We have this xView one I created earlier, which will contain our xView images. And to create a new volume is really easy. You just create it, give it a name. And then once you want to use it, then you hop into your workspace. You go to the resources tab up here in the top left. And then you add your volume, which I've already done here. And then finally, you go over to the libraries page where all the data was. And then at the top, we have a volumes tab. And in here, we can access the volume that we created. And you can see I've already uploaded some of our files. These are the backgrounds that I created with the script, along with the metadata that's created alongside them. The script will generate metadata based off of the background file itself, the image. And that'll be useful for simulating the sun and using things like latitude and longitude. But it's really easy. You can just add a file in like that, and then it's available to be used in graphs. If we go back to one of our graphs here, we can see that we're using one of our volume nodes. This is our backgrounds directory, which we have in our volume. You can create those using this volumes tab. And you can just bring in those files that you've uploaded. You can bring them in individually, or you can use all of them at once. And so now that those are in here, they're just going to act like those air-based backgrounds that we were using before. And when you use those to generate backgrounds, to generate data, it'll end up looking like this. And so here's some of the data that we've generated, and I can highlight the objects we've added. Is these tanks and different AFEs have been put into the places where objects used to be. And so we've got this nice, clean urban environment, but we've also added in our own objects. These are synthetic objects, synthetic 3D objects that have been superimposed into the image, and the lighting that's been applied to them has been informed by the background metadata. And so it's pretty straightforward to just run this script, upload the output into uh, your organization on the platform, and then just get ready to use them. So yeah, that's the new workflow we've developed, and we're always hoping to increase the usability of our platform, the way in which folks will add their own data and be able to do their experiments that they'd like to do. And so, hope to talk about some new technologies we come up with soon. I think that basically covers it. So I will turn it back to Chris for the question section.
All right. Thanks very much, Dylan. That was great. And so just so everyone knows, we will be happy to take some questions. There are a couple already in the queue, and I am just going to start sharing here. Share. There we go. And so actually, I just hid the questions. So let me pop them back open. So far, we've got two, both from Vikash. Vikash, we really appreciate the interaction here. Um, I'll start out with your first question. And so your question was, is it fair to say that companies like Black Sky, whom we mentioned today, use our services to train models on kinds of imagery that are not possible or are prohibitive to obtain in real life? And those are exactly two of the reasons why our customers do use us. In some cases, our customers are putting up a novel sensor type that just isn't in the sky yet or isn't deployed in the field yet, and they want to generate physically accurate imagery to start to train algorithms and develop AI pipelines before they're actually deploying that sensor. And in some cases, feedback from interaction with the synthetic data may actually inform the design or the specific implementation deployment of those sensors. So absolutely, cost and then just yes no binary ability to obtain certain types of real sensor data or real sensor data with certain objects of interest are both reasons why customers use us. Okay, so Vikash asks another question here. What is the relationship between channels, graphs, and sensors, such as optical, SAR, and LiDAR? So maybe I'll have Dylan answer this question. And Dylan, one thing that you might want to address is the fact that a channel can actually have multiple sensors in it. So Dylan, do you want to speak to the differences between channels, graphs, sensors, and their relationships?
Sure. Yeah, so a channel would be the base application that can cover the domain that you're trying to create data for. And so in the instances we were showing earlier in the demo, it was a satellite viewpoint, so top-down orthographic. But the nature of the sensor can vary. In that one, it was color, just regular optical sensing. But within a channel, you can have different sensors, as Chris mentioned. And so you could do different sorts of SAR or MWIR, things like that, different modalities, and those would be contained within the graph. Is with the graphs I was showing earlier, they were using the RGB color sensor, but with another channel or even within the same channel, you could have multiple sensor nodes and do things like modification to them. And so a channel contains graphs, and in those graphs are sensors, and there can be multiple ones in there. So hopefully that answers the question.
Okay, great. Yep, that's great, Dylan. One other note is we provide an actual open source framework that helps developers to basically wrap simulators and descriptors for content in kind of common patterns. And these terms like graphs and sensors channels, they are embodied in that framework. We also, our customer success team, including folks like Dylan, actually sometimes gets engaged and does some or most of the work for a customer to build out their channels. So we fully acknowledge that a lot of folks who have computer vision shops don't have a lot of expertise in 3D simulation, game engines, that kind of stuff. And so when needed, we can actually step in and help there. Okay. So it looks like Vikash has one more question. And this is actually a great question because it touches on something that we get asked a lot, and I'll talk to it a bit. So Vikash, your question was, could we list down the set of pre-trained models available on our platform? In fact, we don't train models today for use by customers. Typically, our customers are the experts in training the models they need for their own specific business purposes. So most of our customers today use our platform to generate data that they are then integrating into a pipeline or downloading and using in a uh, in a um, in a they're downloading using in a training scheme, and they are so they are training their models. We can't be more expert at training their models than they are. We are actually exploring, because of customer demand, some capability around model training and inference, and we will have more information on that as it becomes. And then Vikash asks another question, which is, does this mean that we use traditional software like physics rule engines to generate images? Yes, absolutely. If I scroll back up to this slide, for example, so we work with NVIDIA Omniverse, which is a ray trace rendering tool that operates on a 3D physics world, digital physics-based world. Uh, RIT's DARES lab produces a simulator for government that was funded by government research grants that is one of the most physically accurate simulators out there, that's been productized for generating a wide variety of sensor modalities, hyperspectral, multispectral. They can do some types of SAR. ANSYS, massive multi-billion-dollar company that does engineering simulation tools. Quadradox is Duke spinout that builds X-ray hardware, and then they built their own novel X-ray simulator to emulate their specific hardware configuration. And of course, we partner with Esri for things like access to imagery services that can be brought into the platform. So generally, what we're doing is helping customers piece together 3D models, 2D backgrounds, and other 2D information, and then combining those into scenes that are processed through simulators, such as some of these. All right. Are there any other questions from the audience? If not, we are super happy to have presented to everyone. Oh, one more question here. Can we elaborate on how sensor configuration, such as SAR configurations, plays a role in your product? Yes, absolutely. Dylan, I'm going to go back down to the slide here. So Dylan showed briefly the drag and drop interface for node-based graph construction that is the configuration interface for synthetic data jobs. In those nodes, what you'll find is a channel-specific set of parameters that can indicate variable parameterization for everything from time of day to specific sensor configurations down to which wavelengths are being collected. There are, for some customers, we've helped them implement specific parameterization around sensor timing, so collection timing. Some sensors collect everything nearly synchronously. Other sensors, for example, some line-based scan sensors will collect line by line, and you end up with a time delay between those line collections. And so sensor configuration is integrated. The ability to actually change sensor configuration is actually integrated into the metaphor that we use for driving configuration in channels. Typically, what you'll find is that not all RGB imagery is the same. So you may find a more diverse set of parameterization in one channel that was developed for one set of applications than in another channel that is collecting a similar type of imagery, but which didn't actually need that level or depth of parameterization. So hopefully I answered that question. Okay, we're very happy to have you on. Thanks for the comment, Brooke. And Dr. Flaxman, we will definitely be sending a follow-up email with the video recording, and we can make a PDF of the slides available as well. So unless there are any other questions, we are super happy to have had you join us today. The easy ways to get in touch with us, of course, are to visit the website. You can contact Dylan or me. It's just Chris at Rendered.ai or Dylan at Rendered.ai. You can always, of course, go through our sales at Rendered.ai channel or email address. And then anybody can actually sign up for a free trial and pick one of those sample gallery items that Dylan showed off and actually get a workspace instantiated in the platform that for most of them where you could even reconfigure, run, and generate a data set yourself. So unless there are any other last questions, I'm going to go ahead and say thank you very much to everyone who attended, and we hope to see you soon on the next webinar on August 22nd. Thank you.